Welcome. Today we're going to introduce logarithms. But before we do that, I want to emphasize why we're going to introduce logarithms. Up to this point, we've been able to solve equations, even quadratics, for hyperbolas, ellipses. Let's look at this simple equation right here, 3x plus 2 equals 9. I've already solved it, but what I want to emphasize is that to solve it, I do the opposite operation on each of the numbers that are being combined with x. Like for instance, I'm adding 2, so I minus 2 from both sides to get 3x equals 7. Opposite of addition is subtraction. Then I had 3x equals 7. To undo the 3 times x, I divide by 3. So I do this division, and I get a final solution of 7/3, which is perfectly fine for a solution. Now here we have x squared equals 9. Well, how do we undo a square? Well, we do its inverse operation. There's actually a 2 right here. We just don't write it. X equals the square root of 9. And we know what that answer is. That's 3. But wonder if we had x squared equals 5. Well, we still want to be able to solve this or isolate the x, get rid of this operation of a squared. Well, we do that by square rooting 5, which we might not know off the top of our head. So I grabbed a calculator and I square rooted 5 and got 2.236, so forth. And it keeps going. It's an irrational number. So we're still able to solve for x. Wonder if I had x raised to the 5th power. Again, I can solve that. X to the 5th power, equaling 88. Well, I can easily do that. What I do, and I need to make an adjustment here, that's not equal to that. To solve that, I take this 5th root of 88. So again, x would equal, that's what I meant to write here, x is equal the 5th root of 88. Now again, we've learned how to write roots as irrational exponents. So I could actually write 88 to the 1/5 power, because remember the denominator is a root, and I can do that on a calculator. Either the 5th root of 88 or 1/5 power of 88 gets 2.448. Now, here's where logarithms come in. Wonder if I had 3 to the x power equals 9. I don't do the 3rd root of 9, and I don't do the xth root of 9. That doesn't get x by itself, right? So this doesn't work. Now we do know what the answer is. We can think to ourselves, well, 3 times itself, how many times is 9? Well, it's 2. So we do know the correct answer is x equals 2. But how do I write this without actually doing the math? In other words, write the operation. Well, what I'm going to do is show you how to do that. I'm going to erase this for just a minute, and we are going to rearrange this expression as a logarithm. And how we do that is we introduce a new symbol, and the symbol is 3 letters. And so we're always going to use these 3 letters. Not always, but I'll explain when we don't. But for right now, we always use log, log. Now, we're going to take the log of our outcome that we want to get when we raise 3 to some power. So we take the log of 9. Now, the problem is the log of 9 is going to equal 2 as long as we're talking about 3. So logarithms have a base. We do a little subscript of what we want our base to be. So in other words, this is an exponential equation where 3 is our base. Well, our logarithms have a base. It's the same as what our exponential equations would be. That base is a subscript. And so what we've done is, I meant to erase this 2 here. If I didn't know what the answer was, this would actually isolate the x, because now the x comes over to the right side, and we have log base 3 of 9 equals x. Now, think of how this is meant. This is saying the log of 9 base 3 means if I have a base of 3, what exponent would you put on 3 to get it to equal 9? So it's really just an exponential equation. And when you solve that, you get 2. So when I come over here to the log, or 3 raised to the x equals 17, if I don't know what that is, I have no clue how many times I got to multiply 3 by itself to get to 17. So what I can do is I can write it as a logarithm. I do a log base 3 of what I want to get, which is 17, and that, whatever that is going to be the exponent I need. So the exponent is isolated as a variable x. I have to do a base 3 on the log to 17 because there's no reason I couldn't do 2 raised to the x equals 17. Well, that would be a completely different logarithm. So I still do the word logarithm, or log, but now I'm doing a base 2 equals x. Oh, sorry, I forgot the 17. Log base 2 of 17 equals x. Of 17 equals x, which gives me a completely different number than if I did log base 3 of 17. So I'm going to grab a calculator and do that. So I just quickly did this on a calculator, and what I found out is that the log base 3 of 17 is 2.5789. Now, if you're unsure or you want to verify that, take 3 on a calculator and raise it to the power of 2.5789, and you'll get basically 17. This is a decimal that actually keeps going, and I had to round it. Okay, same thing here. I took the log base 2 of 17 to find out what value of the exponent needs to be on 2, and I got 4.0875. And again, and I rounded. So if you put 2 raised to the 4.0875, you will get approximately 17. So this is how we isolate the variable that is an exponent on an exponential equation. Now I'm going to rewrite this really quickly. So I quickly rewrote these expressions in an algebraic form, meaning just letters. Any base number raised to an exponent will equal another number. By the way, the base will always be positive. We won't use negative bases. So b will always be positive. But the log of any number, any number b raised to the exponent, as long as b is positive, is equal to some number, other number n. We can rewrite that as a logarithm base b of the n value will equal, not b, will equal our exponent. Wow, not b, will equal our exponent. It's how we isolate the exponent. It's how we get the exponent by itself. If you have any questions, please bring them to class, but just write this down and it should allow you to do your first assignment.